Welcome to lecture 2 for day 7, where we'll continue with hormonal regulation. Now we're shifting though from neural regulation we talked about last time with short-term regulation of blood pressure via autonomic reflexes, and now we're going to talk about longer-term regulation of blood pressure with hormones. You know the drill. I think the only thing sciencey about our memes anymore is that they're presented within a science lecture. But anyway, we got a grouping of quarantine memes here. So we have in the top left. I like how ads have gone from buy a Toyota to this is a difficult time and uncertain time for all of us. Buy a Toyota. And then top right here, we got how TF are people supposed to make this face when I walk past them if I got a mask on? Good question. And bottom there, hopefully this isn't me or you, but waking up 30 seconds before my Zoom meetings every morning. We'll begin today by describing the components of the renin-angiotensin system, or RAS, and the ultimate effects of angiotensin II on blood pressure. There are several hormones that help regulate blood pressure, and some that you're familiar with. Here we have epinephrine and norepinephrine, and others that may be new to you, such as aldosterone, angiotensin II, atrial natriuretic peptide, and antidiuretic hormone. What they all have in common is that they work to regulate blood pressure by altering resistance, blood volume, or both. So these hormones work by altering blood volume or resistance. And recall that resistance involves changes in vessel radius. The other components of resistance, remember, were vessel length and blood viscosity. Those can affect resistance, but really those are more static and they don't change too much. Now, altering blood volume, which some of these hormones do, that may be less clear though at this point. So let me ask you this. What are the ways in which we alter blood volume? Well, one of the things we can do is we can stimulate fluid intake. If we intake more fluids, that's going to raise our blood volume. Or we can change our urine output. We can urinate more or less in order to alter our blood volume. The renin-angiotensin system, or RAS, falls somewhere in between short-term neural regulation and long-term hormonal regulation. And that's because the synthesis of angiotensin II is initiated by the nervous system, which is short-term. Okay. And angiotensin II causes release of other hormones that we see here. And these are long-term mechanisms of blood pressure regulation. I tend to be a visual storyteller, so we're going to work through this RAS, which can be a bit complicated, in a visual manner. We'll now work through the renin-angiotensin system, the RAS, step by step for clarity. And this is going to begin with the liver, and it's going to continuously produce a protein that we call angiotensinogen. Angiotensinogen is an inactive hormone, so it's a precursor hormone that's secreted by the liver. And this is continuously released into the blood. While angiotensinogen is continuously produced and released by the liver, meanwhile, renin, an enzyme, is released in response to low blood pressure, and that's detected at the kidney, or sympathetic stimulation. So this little guy here is representing a sympathetic response, fight or flight. Now, either of these will trigger the release of renin from the kidney into the blood. All right, if you want to pull out your worksheet, we can start piecing together the events involved with the RAS. So we started with angiotensinogen being continuously produced and released by the liver into the bloodstream. And that's that inactive hormone, and that's going to be represented here with these purple triangles that are shown. Okay. But then we said simultaneously, the kidney receptors, whether detecting low blood pressure or they're stimulated by a sympathetic response, they're going to release that renin enzyme into the blood as well, and that's shown by this green enzyme here. And then renin, it's an enzyme. It acts to convert angiotensinogen, that inactive hormone, to angiotensin 1, another form of inactive hormone, and that's represented now by these light blue triangles. Now, angiotensin 1 is still an inactive hormone, so it's going to need conversion to form an active hormone. And this takes place primarily within the pulmonary capillary endothelium. So here we have the lungs, pulmonary capillaries specifically, and we're going to look at the endothelial layer, which is that innermost tunic of our vessels of the capillaries here. And within that layer, we have angiotensin converting enzyme, or what we call ACE. And if we break down this name, it tells us what it's going to do. We're going to convert angiotensin into that active hormone form. So we have our angiotensin 1, the light blue triangles there within the blood, within this capillary. And then it's going to interact with this angiotensin converting enzyme that's found within that endothelial wall. So we see that most of the conversion of angiotensin 1 to angiotensin 2 by this angiotensin converting enzyme occurs within the lungs. So I'd like for you to think, why does this location work well? Why have most of this enzyme concentrated within the pulmonary capillary endothelium than the lungs? Well, this works well because all the blood within the body moves through capillary circulation in order to be oxygenated. So therefore, it maximizes contact between angiotensin 1 and angiotensin converting enzyme, or ACE. Back to our figure then here that's found on your worksheet, and you can continue to follow this in. So we said that we have angiotensin 1, this inactive hormone within the blood, and then angiotensin converting enzyme, ACE, is found in the walls of the capillary, the endothelial layer of those capillaries within the lungs. So within the lungs, within the capillaries, that's where our angiotensin 1 moving through the blood is going to encounter that ACE. And ACE is going to convert angiotensin 1 into angiotensin 2. Now we have an active hormone. Hey, but that doesn't answer the question, how does angiotensin 2 help increase blood pressure? Angiotensin 2 acts as a powerful vasoconstrictor. Okay? And in fact, its effects are much greater than norepinephrine. In the last lecture, we talked about the neuroregulation of blood pressure and how norepinephrine can lead to vasoconstriction. Well, here those effects are multiplied with angiotensin 2. So we effectively narrow that vessel diameter or radius, and that increases the resistance of flow of blood, and therefore our blood pressure is going to increase. Another effect of angiotensin 2 is that it stimulates the thirst center within the hypothalamus. And if we stimulate the thirst center, you are thirsty and you're going to actively seek out more fluids. And fluid intake increases your blood volume. Last semester, we learned that the hypothalamus is involved in homeostasis, and that's performed by the autonomic nervous system for some functions, including body temperature or sleep patterns, or our area of interest, the food and water intake. Now, when we mention the hypothalamus and the thirst center, we're talking specifically about this anterior nucleus, and that houses the thirst center. Finally, angiotensin 2 acts on the kidneys to decrease urine formation. So angiotensin 2 has this direct effect within the kidneys to increase sodium reabsorption. And if we reabsorb sodium, that causes water retention. And we're going to talk about this more within the renal unit at the end of the block. But basically, less fluid lost from the blood due to sodium retention means we can maintain our blood volume. Okay. And then there are indirect actions of angiotensin 2 as well, and that is that it can stimulate release of aldosterone and antidiuretic hormone, or ADH, that we'll talk about next. We'll now turn to the effects of aldosterone and antidiuretic hormone, or vasopressin, on blood pressure. At the start of this lecture, we said that angiotensin II leads to release of other hormones. And one of its indirect actions is to stimulate the release of aldosterone. So let's turn and look at this now. I think I've been saying aldosterone up to this point. I apologize. So the first thing we're going to note here, if we're going through the RAS and find our way to aldosterone, is that we're going to see a drop in blood pressure. That's going to be detected at the kidney, which we said releases that enzyme renin in response to that drop in blood pressure. And remember, simultaneously, we have our liver over here that is secreting angiotensinogen, that precursor inactive hormone. And it's continuously doing so. And then our enzyme and our precursor hormone interact to give us angiotensin 1. Okay? And that angiotensin 1, we then said, is converted by ACE, angiotensin converting enzyme, within the capillaries of the lungs. That'll give us angiotensin 2 now, the active hormone, our product, and that is going to trigger aldosterone release from the adrenal cortex. So here's our adrenal cortex, and we're going to release aldosterone. Well, aldosterone, that works to increase absorption of sodium. And if we increase absorption of sodium, simultaneously we're going to retain more water. We're going to decrease the loss of water from the body, and we're going to increase our blood pressure and our blood volume. So our blood pressure is going to rise by decreasing our urine output. All right, next we have antidiuretic hormone, or commonly called vasopressin. And you can probably guess what this hormone does based on the name. We have that prefix anti and then diuretic. So diuresis is producing excess urine. A diuretic is something that makes you urinate. So if we have an antidiuretic, well, you're going to urinate less and you're going to retain more volume. And that's probably going to increase your blood pressure. So it helps to maintain or elevate your blood pressure. And the way this works is either low blood volume or angiotensin 2. This is another indirect action of angiotensin 2, can stimulate the posterior pituitary to release ADH, or vasopressin. Okay. We're going to revisit this slide real quickly so I can show you the posterior pituitary and the hypothalamus once more. So the posterior pituitary, it's going to release antidiuretic hormone following stimulation by the hypothalamus. Okay? And it's actually within the hypothalamus that we produce antidiuretic hormone. It's actually within this supraoptic nucleus. So it's made within the hypothalamus and then stored within the posterior pituitary. Then when the hypothalamus is stimulated, either by low blood pressure or angiotensin 2, the posterior pituitary releases that antidiuretic hormone into the blood. Returning then to our image here, we had either low blood volume or angiotensin 2. That's going to stimulate the hypothalamus to trigger the posterior pituitary to release the antidiuretic hormone, or vasopressin. And antidiuretic hormone, that's going to act to increase absorption of water at the kidney, which decreases our loss of urine. And that helps maintain our blood pressure and blood volume. In short, then, we say that ADH, or vasopressin, increases water resorption in the kidney. We see less fluid loss, which helps maintain our blood volume. Secondly, it also stimulates that thirst center within the hypothalamus, and that fluid intake is going to increase our blood volume. And finally, in instances in which the body is experiencing extremely low blood volume, we're going to see a large release of ADH. So let's say we have a blood hemorrhage, and this is going to lead to very low blood volume levels. Well, we're going to see this dump of ADH that leads to vasoconstriction. That vasoconstriction is going to increase resistance and therefore blood pressure, to increase our blood pressure to counteract that low blood pressure due to the hemorrhage. Because of this vasoconstrictor ability, it is also termed vasopressin. That's where that arises from. So in summary, we see that all three, angiotensin 2, aldosterone, and ADH, can decrease urine output to maintain our blood volume and pressure. We then see that angiotensin 2 and ADH additionally can increase peripheral resistance and therefore increase blood pressure. And they also can further increase blood pressure by increasing or at least stimulating fluid intake. And we'll revisit these hormones and their actions in the renal unit coming up. Now for the role of atrial natriuretic peptide in regulating blood pressure. So far we've been talking about ways to raise our blood pressure, but what if it needs to be lowered? Well, this is the role of atrial natriuretic peptide, or ANP, that helps decrease blood pressure. Okay, so let's say we have high blood volume, high blood pressure. Well, when this happens, the atria of the heart are going to be overstretched. And when those atria are stretched by high blood volume, we're going to release ANP, atrial, that's where the atrial comes from, natriuretic peptide. Okay. This does a couple different things. The first is it stimulates vasodilation, which is going to decrease peripheral resistance, TPR for short. The other thing it does, it's going to increase urine output. So we're going to see increased excretion of sodium and water, and that's going to help lower our blood volume, lower our blood pressure. And finally, a little bit on mean arterial pressure, or MAP. We see then that maintaining normal blood pressure is dependent upon three variables, and those are cardiac output, resistance, and blood volume. These are all directly related to blood pressure, and you can see that an increase in any of those would directly increase your blood pressure. So, for example, increasing cardiac output raises blood pressure. Increasing resistance raises blood pressure. Increasing blood volume raises blood pressure. Okay, and on the flip side then, a decrease in any of these will decrease your blood pressure. We just said that blood pressure is regulated by controlling cardiac output, total peripheral resistance or resistance, and blood volume. And mean arterial pressure is the blood pressure that we're interested in. This is what's being monitored and regulated within the body. It's the main driving force for propelling blood to the tissues. Now, there are two primary determinants of mean arterial pressure, or what we'll call MAP for short. And they are cardiac output and total peripheral resistance. And a number of factors determine cardiac output and total peripheral resistance. And we're going to review the factors that affect MAP at the beginning of class tomorrow. All right, here we have a flowchart of the main factors that influence MAP, or mean arterial pressure. And we're going to begin class tomorrow by filling this in. So if you print off your worksheet, that's helpful. Otherwise, you can just scribble it into your notebooks. And we'll walk through together the different factors that influence MAP, and then we'll apply them to a couple case studies.